Okay, in the next several videos, I'm going to review models and discussions from Heck et al.'s book, Multilevel and Longitudinal Modeling with IBM SPSS. We're going to look at Chapter 3, and basically in that chapter, the authors incorporate or basically analyze data using school level data. Basically, you've got a data set here. And by the way, you can download that data set at the publisher's website right here. So that's where it's coming from. And so basically you have a variable called school code. So there are 419 schools. You have student identifiers. So these are the students with their identification codes across schools. These are identifiers within schools for each student. This is their gender ID, so coded 0 for male, 1 for female. Student level socioeconomic status. There's math achievement, which is basically the dependent variable in their models. Then you have school levels of socioeconomic status. So basically taking all of the SES for students in a given school and averaging them out. So these are school level SESs. And SES is also essentially centered. You also have proportion of students who are basically expressing an intention to go to four-year college. So this is a proportion within school 1, within school 2, and so forth. So, and then you've got whether the school is public or private. If it's a private school, it's coded 0. Public school is coded 1. So the first thing that the authors do in the textbook is they kind of discuss some of the research questions that one might be interested in addressing. So I've kind of, some of these are quotes and some of these are just summaries of what they were basically driving at. So one question, does student math achievement vary across schools? The second, is there a relationship between student SES and math achievement? That's basically at level 1. Does the effect of SES on math achievement compound at the school level? So basically looking at sort of school average SES and whether or not that might have an impact on math achievement. And then also, do other school level compositional factors predict achievement as well? And then, do the slopes for the relationship between student SES and math achievement vary across schools? So in other words, are we going to observe significant variation in slopes across school? And then also, are there contextual factors that might predict variation in those slopes? So the first illustration that the authors really begin with is just running a single level regression analysis. Oftentimes it's the case that researchers will kind of ignore the fact that observations are clustered within higher level units like schools or classrooms and so forth, and they end up just running just a standard least squares regression analysis. So here we have just a simple regression equation where scores on math achievement, which is the YI, so that's the individual student score on math achievement, is a function of socioeconomic status. Basically, the equation is laid out where you have beta subscripted 0 is referring to the intercept of the regression line. Then you have beta subscripted 1 is just the regression coefficient for SES. So we're multiplying the regression coefficient times each person's score on SES or value on SES plus a prediction error for that observation. So the prediction equation is just essentially removing the prediction error, and so you have predicted score on Y as a function of the intercept for the regression line plus the product of the regression slope times each student's SES. So to run this analysis in SPSS, you can see I'm kind of laying it out right here and how you would do that. And I'll just kind of do this in real time to illustrate. So we're just going to go to Analyze, Regression, Linear, and we'll put SES, which is the student level predictor, level 1. predictor of math achievement, which we'll put math right here. And then so when we click on OK in SPSS, you can see that we've got the model summary table. So the R-square value is 0.14143, indicating that essentially SES is accounting for approximately 14.3% of the variation in math achievement. The R-square value would be deemed as statistically significant. And looking at the individual regression coefficients you see right here, this is the slope for the line, which we could substitute into that previous equation for beta 1, and here's the intercept for the line. The intercept is just a predicted value on y when your x predictor variables are equal to 0. Given that SES was centered at 0, basically what that would tell us is that when students are scoring at the mean on SES, the predicted math achievement score is 57.598. So essentially, this is just kind of redocumenting what I just said. And the thing to note is that essentially the intercept in the model and the regression coefficient for beta 1 right here are treated as fixed parameters. So in other words, we're not considering the possibility that the intercepts or the slopes vary across schools, but rather that they are fixed across school contexts. And one of the problems with this type of single level analysis is that the intercepts and slopes may actually vary across schools, and that variation may be a substantive area of interest by the researcher. Additionally, you also have the possibility that you also have the likelihood or increased likelihood that because of the clustering within schools, you have correlated residuals. And that oftentimes will translate into deflated standard errors when you're testing the regression coefficients and an increased likelihood of committing a type 1 error. So this is just kind of an illustration. Essentially, I just went ahead and ran this based on the description in the textbook to illustrate what the relationship between SES and math achievement when you're not considering schools, and then the relationship if you consider school context. The authors actually illustrate this in their textbook, and I'll just show you how I generated both of these plots. So if I go under graphs and legacy dialogues, I'll go to scatter dot right here, click on simple scatter, and I will move SES over to the x-axis, and I'll move math over to the y-axis. And when I click on OK, I get a plot. Now you'll notice right here, this is the plot across all 419 schools. So it's kind of a mess. Let's just do it for the first 80, which is what they kind of used in their illustration. It was basically, or the first 80 cases, I should say. So what we'll do is I'll just go under data, select cases based on time or case range. I'm just going to say range of observations from case 1 all the way through case 80. Click on continue and then on OK and go back to graphs, and let's do this again. So again, simple scatter, define, these are already set. So if I click on OK, there's the plot of data points, and it looks like there's a pretty good positive correlation between these two variables, where basically as scores are with students with higher SES tend to exhibit higher levels of math achievement, lower SES, lower levels of math achievement. If I double click on this and then click on the little add fit line at total, I get the fit line, and that's what it looks like. So that was the first picture that you saw right here. Then for this one, I'm going to look at it by school. So I'm going to go to Graphs, Legacy Dialogues, continue on with the same specification, but now I'm going to add school code, which is our school level identifier. I'm going to click on Set Markers By, and then on OK. And so now you can see it looks like little colored dots reflecting each school. And basically, if I want to get the lines for each of those schools, I can just double click here and then go to add fit line at subgroups. And when I click on that, you can see I've got all these lines appearing. I really don't like to have the equation in here, so I'm just going to click attach label to line, click that off, and then apply. And so now you can see the individual regression lines. So you'll notice that essentially, each of these lines, you can see that the slopes appear to be varying. You can see that this yellow line right here, it appears to be quite substantial in terms of the positive relationship, whereas some of these lines are less strongly positive, and even this red line right here looks like it's a slightly negative relationship between the two variables. You'll also notice that remember what I said, that the intercept of the regression line is essentially the predicted value on y when uh, your x, uh, your predictor variables are equal to 0. And we essentially, this variable right here, SES, was already centered to begin with. So this is basically where the intercepts would be for each of those lines. And you can see that they appear to be crossing over in different locations. So in other words, there may be some evidence of variation in intercepts across schools, and then you also have variation in the slopes across schools. So for that reason, it makes a little bit less sense to carry out standard least squares regression with this kind of data. Okay, so the authors lay out some general steps in developing a multi-level model, and so with two levels. And so basically, level one is specifying and testing a null or no predictors model. So in other words, trying to determine if there's significant variation across the level 2 units in terms of the intercepts. Step 2 is to specify and test a level 1 model, and then step 3 basically involves adding in predictors at level 2. And then there's certain amounts of possible iteration that can occur between 2 and 3. So the first model that the authors discuss is a variance components model, and basically when we move into talking about multi-level modeling, we talk about equations at different levels. Okay, so the level 1 equation that you see right here, you'll notice it says Yij, and the I and the J is reflecting person I and group J. So in other words, in our data set, we have schools. We have 419 schools. So you would have person I in one of those 419 schools. Their math scores is equal to, and you'll notice that we have the intercept for a given school plus the deviation between the student's score on Y, or math achievement, and essentially the mean for that school. And just to kind of drive home this little point about the intercept in this model being equal to the mean for a school, if you go back and you think about the least squares equation and the computation of the intercept for the regression line, for a simple regression, it would be the mean on y minus the slope for the regression coefficient times the mean for x. So, if you set the slope to 0 and essentially take out the predictor x, you're left with the mean for y. And so, essentially, in the null or no predictors model, we're talking about the intercepts for each group is going to be equal to the mean for each group for the dependent variable. You'll notice that the prediction error component is just simply then the difference between the group intercept or group mean and each individual score within that group on the dependent variable. The level 2 equation is laid out in terms of the intercept. Okay, and so you'll notice that the intercept for group J is equal to the grand mean of the intercepts across the groups plus the deviation between the group intercept, and the grand mean of those intercepts. So essentially, the variance components model is nothing more than carrying out a random effects analysis of variance. And through substitution, we can create a mixed model. So essentially, this equation down here is just taking this part of our level 2 model, which is modeling the fixed component, which is the fixed intercept. So it's the average of the intercepts across the group, plus the random component, which is the deviation between the group intercept and the grand mean of those intercepts. So if I substitute this part for into this part of the equation right here for at level 1, we'll end up with a mixed model that contains both the fixed component, a level two random component, which is capturing random variation of the intercepts around the grand mean of those intercepts, plus a level 1 component, which is the residual at level 1. So the first model, the Null model, is basically just addressing the question, does student math achievement vary across schools? And so I'm kind of walking you through these steps right here, and I'll quickly illustrate this in SPSS. So we'll go to Analyze, Mixed Models, Linear. We'll put school code, which is a level 2 variable or identifier, into the subjects box. Click on Continue. We'll add math to the dependent box, and we're not going to add any covariates. So we'll click on Fixed. Notice that there are no predictors. We're not moving anything over to the model box. This box needs to be checked because this is essentially instructing SPSS to estimate the fixed effect at level 2, which is essentially the grand mean of the intercepts. Okay, so in other words, it's basically the grand mean on math achievement. So we'll go to random, and here we'll now click on include intercept, and we'll move the school code over to the combinations box. And you'll notice that where it says covariance type, there's a little box right here that gives you a number of different options. Because we really aren't including but one estimate of the variation of the intercepts across groups, we'll leave it as variance components. Under estimation, we've got restricted maximum likelihood and maximum likelihood estimation. In the textbook, the authors illustrate running the analyses using restricted maximum likelihood. I'm going to go to maximum likelihood because really, and as they kind of talk about in Chapter 3, they say, well, if you're going to do any kind of likelihood ratio chi-square tests to compare nested models, then it needs to be done then you need to be using the maximum likelihood estimation. The downside of maximum likelihood estimation is in those cases where you have fewer numbers of level 2 units. And in that case, then the restricted might be more appropriate. But I'm going to go ahead and stick with the maximum likelihood. So my results are going to differ probably just a little bit from the results that they provide in that chapter. Under statistics, we'll click on parameter estimates, test of covariance parameters, and covariances of random effects. So now I'll click on continue and then on OK. And so right here you'll see that in terms of our effects, you'll notice that here's our equation right here, the mixed model. So you have the fixed effect for the intercept. So in other words, this is the average of the intercepts across the schools. So we're estimating that parameter. We're estimating also the random effects for the intercepts. So this is basically using a little bit of the notation from the text, which is basically the variation between groups in terms of the intercepts, or basically the group means. I've also denoted it as variance of the mu OJs, or mu 0 J's, which is again reflecting the deviations of the intercepts from the grand mean. So that's this part, the variance of the group effects. And then we also have the within group variation or within cluster variation here, which is essentially capturing the variation across all of the cases in terms of their deviations of y from the group means. Okay, so we have also information criteria, which is generally used to make comparative judgments between models. As I said before, the authors indicate that you should be using ML estimation if you're going to be doing that. So in chapter 3, they don't really spend any time discussing comparing models using this criteria here. But you do have the fixed effects that's denoted here. So just kind of scrolling, just to give you a kind of an online view of this, you can see you have a general test of the fixed effects, and then you've got the actual regression coefficients, the test for the regression coefficients. So you have right here the intercept, which is 57.21. So that is your gamma subscripted 0, 0. So that's not very good at drawing gamma, but that's a little gamma subscripted 0, 0 is equal to this value. You'll notice that there is a standard error and a significance test for this, and this only makes sense if you feel the need to test the intercept against a null hypothesis, which is that the grand mean of the intercepts is equal to 0. A lot of times this is really not terribly useful, and so really that's not particularly useful here. Down here you have the covariance parameters and the estimates. So this is basically an estimate of the variation in the level 1 residuals. So basically taking this is the variance within clusters, or you could say the variance of the residuals with a little ij right here. And then you also have the variation in the intercept. So this is the variation in the mu subscript 0j. So so this is the between variation. So you could say variation between, or we can just say variance of the mu and a little subscript oj or 0j right here. You have a significance test of the variances, and this is oftentimes useful for determining whether or not you should even be carrying out so you typically would use this to evaluate the significance, and then oftentimes if the if variation in the intercepts is statistically significant, then you would take that as an indicator of significant variation across groups, suggesting possible clustering, and you may want to account for that. You'll notice here that that it's not statistically significant, and the reason why is because I failed to turn off the select cases button. So this was basically my goof. I'm going to go back to all cases, and we'll rerun this to be consistent with the text presentation. All right, so kind of getting back to this, and we have there's our intercept. We're not really interested in whether or not this is statistically significant. You can see then that we have these are the p-values for the test of these parameters. So you basically, again, we have the within variation or variation of the level 1 residuals, and then we have the between variation of the intercepts. And so you can see that both of these are statistically significant. In your textbook, the authors kind of discuss the fact that it doesn't really make much sense to utilize a z-test where you can essentially test, theoretically, you could test using a two-tailed criterion, and it doesn't really make a whole lot of sense because you can't have a negative z value. I mean, you can't have a negative variance estimate. So what they kind of suggested is that you can take whatever the p-value is that's printed out here and basically divide it by 2, and that will really be the appropriate p-value to use. In both of these cases, though, we are basically saying that there's significant variation at level 1 and at level 2 that remains to be explained. So really the p-values right here, it's pretty irrelevant. Both of them are less than the conventional 0.05 threshold, so we would reject the null hypothesis. The null is essentially that the variance, each of those variance components is equal to 0. So the alternative being that they would be greater than 0, and so we would reject the null hypothesis in both cases and conclude that there is significant variation at level 1 and then at level 2 that can be potentially explained through the addition of predictor variables at those levels. So at any rate, that is typically the first step in multi-level modeling, is testing a null model, and then we're going to move on then in the next step to testing by adding in a level 1 predictor.